So, we are in the fourth lecture of this week, that is fourth week, and now we are talking about a special application area, that is sensor system for PHM of electronics. In fact, the electronic industry has caught up with this development, though not at a advanced rate, but it is initiated actually. Use of, as I mentioned, PHM still is at the laboratory level, and electronics industry is one of the active industry which is trying to use it. One more reason for electronics is it is comparatively easier to go for PHM of electronics, because compared to the mega system like diesel generators, or any generating station generator, there are huge systems, so their resources also are required. But in electronics can be managed relatively easily, though they have at material level they also have a lot of complexity, understanding of upgradation mechanism, So, but then our fourth lecture will be on PHM of electronics. In fact, I am planning to have PHM of electronics and PHM of mechanical engineering. So, mechanical engineering, when we have a separate week for that, we will discuss, and PHM of electronics. An overview I will give you this in lecture. Many case studies will be covered in our later lectures. So, as I mentioned, environment. In fact, environment is even for mega structure it is there actually. Why? Because suppose if we have a humidity and then there is a structure at the coastal line, and then we have along with the humidity the CO2 concentration, then carbide, the carbon formation at the layer, and that is degrading the structural strength to the level or millimeter level, deep into the concrete, that affects the strength of the. But as far as electronics is concerned, the temperature, humidity, apart from quality, they are the major contributor to electronics, and of course thermal fatigue. These are some parameters. Thermal fatigue is an operation mechanism, okay, but then environment is one of these two parameters, that is temperature and humidity. They are one of the severe degradation mechanism, or electronics are susceptible to these two mechanisms. Maybe many more, but these two are. So, with that we talk about the electronics. Often there are two classes of monitoring. One is life consumption monitoring, and then second one is data driven health monitoring. Of course, there is third one also, that is integrated fusion technique, where we integrate fusion technology with a data driven method. So, as I said, the POF model and data driven model, they in principle tend to reduce the uncertainty in prediction of remaining useful life. So, that is how it is. And for common cause failure, dedicated sensors are required, because even humidity can induce a common cause failure into the electronics redundant channels, redundant and diverse channels. Diverse channels have less probability compared to redundant channel. Similarly, increase in temperature, the electronics cubicles where it is like, if we cannot maintain a good ground benign condition, that is 22 degrees centigrade temperature and 50% humidity, the performance of the electronics will degrade, and that will affect our target functions adversely actually. And that's why there is a due consideration in the reliability and safety in the design of electronic system. If I have to like we have one sensor and one channel, to increase the reliability of the complete monitoring signal, there will be 3 sensors, okay, and though right from sensor to data acquisition and actuation function, these 3 channels will be monitoring the same parameter. If it is temperature, it will be monitoring the same parameter. So, why? Because if one sensor fails, it should not affect the system adversely. Of course, capacity will come down. Earlier 3 sensors were monitoring, now 2 sensors are only monitoring. But then reliability or safety is not affected. But if 2 sensors fail, then yes, the system should go to the safe mode. Okay, so that's why they are called having. And then if there is a common cause failure, then all the 3 or at least 2 will go to failure mode. So that's why for common cause failure in the panel itself, there will be temperature monitoring and humidity monitoring systems are there. In fact, airflow monitoring systems are also there. There should not be reduction in airflow. So, and that is again a process parameter. So, that is a kind of built-in safety, reliability is there in the system, especially for a complex system, because the consequences of safety and reliability, especially safety being the overriding factor, it is a no-no for any electronic system, because our subject is electronic system as of now. So, what are the potential precursors in electronic system that we have? See, and the component. So, let us say for our electrolytic capacitor, I would say particularly for aluminum electrolytic capacitor, let us choose this component, and then if this is the component, what are the precursors that we need to monitor to track the degradation? So, one is that capacitance alone, reduction in capacitance is an indication that capacitor so capability is coming down. Equivalent series resistance, of the capacitor, if that increases, that is another parameter. So, and it has been demonstrated that if you monitor these parameters, you can track the degradation mechanism, and that in turn the remaining useful life of the capacitor. Leakage current and electrolyte level. In fact, these two are also extensively being used. In fact, I had a very good experience on measuring the level of electrolyte through X-rays or whatever, or any internal built-up of inside the capacitor, that also, and they reflect in terms of leakage current or equivalent series resistance. Okay. Now we have insulator gate bipolar transistor, IGBT. It's a very important component. In fact, I have listed out only those components which are relatively having more failure rate compared, especially if we talk about the power electronics. Power electronics is a little tricky game. Microelectronics, we have still a lot of built-in quality, reliability and all. But same thing is not true with the power electronics. Power electronics, if we want to have a safe mode, derating is the only mode. If you require a unit of 20 kilowatt, you go for 40 kilowatt or 50 kilowatt, so that the components are less stressed. So, that is called derating, to increase the reliability or safety of the system. So, IGBT, collector emitter on voltage, gate threshold voltage, transductance, collector leakage current, chip thermal resistance. So, these are the things for IGBT, and they are very important device for power electronics as well as microelectronics. Ceramic chip capacitor, leakage current, resistance, dissipation factor and RF noise. And the increase in these parameters will know that our ceramic chip capacitor is a giving problem thing. Though both are capacitor, but both have, other than the you can say leakage current, there is no other parameter. Maybe we can say equivalent series resistance is common. Here it is resistance, here we call equivalent series resistance across the capacitor. Then complementary metal oxide CMOS devices, supply leakage current, supply current variation, operating signature, and then current series noise, and then logical level variation. Because all CMOS devices, they have logic operations on the through the transistors on board, and this kind of things gets reflected here at logic level variation, and then RF noise, radio frequency noise. And then RF power supply, there are something, but somehow I have not given anything because I was not getting pretty confident about those kind of precursor failure. But maybe in future classes, when I do more research, probably for RF power supply, I'll give you something. Then solder joints, delamination, thermal fatigue, these are the two major modes, and they sometimes appear as a crack, or and they are monitored by either voltage or current variation in the circuit at appropriate location. Cable and connector, change in impedance, leakage current, insulation, embrittlement, loss of fitment. So these are the things. In fact, cable and connectors, they when we talk of couple of years of operation, because they are not because of degradation, because they are plugged in, plugged out comparatively more frequently, they are the cause of electronics module failure. So sometimes it is replacing certain isolation component, or sometimes you have to go for large maintenance, replacing the card itself, and then switch mode power supply, which is so common, then all the computers and all, output current and voltage and ripple and efficiency, these three are. Similarly, field effect transistor also, I am still trying to work on what are the degradation mechanism. Probably in the maybe next lecture means next week, I'll cover when we talk about the real time application of electronics PHM. Then criteria for PHM sensor, like here we saw for mechanical also, but here we have measurement, temperature, humidity, dust, and is for mostly they are for environmental monitoring. Then output is voltage, current, and capacitance. These are the things. So input output we have seen, and the measurement quality matrix is accuracy again on top, sensitivity, precision, because they are miniature components. So precision is very important for them, and ranges and resolution. These are the things. Sensor electrical parameters, power consumption. This particular thing, that is power consumption, to have a solution for this. Now the modern sensors, they are having a onboard power management. There will be external supply, but still on board itself there will be in autonomous mode. They will have the power management system, to continue the ability of the sensors to perform its intended function. Now operating environment requirement, ground benign, industrial. So depending on which environment we are operating, our robustness should be built accordingly. If I am having a control room, my instrumentation room should have the ground benign condition. If it is a factory class component, and then the component quality itself matters actually. If I have military grade component, then I can expect a huge good performance, but if in industrial setup, we have to have those kind of specification, otherwise the reliability will not be the same actually in industrial environment. So online sensor monitoring, as I mentioned, for common cause failure should be there actually. Typical configuration of electronic channels in a complex safety critical system. Now we have come to a very specific requirement. Unless until you are able to imagine what is a complex engineering system. So simply I have given the definition of complex engineering system earlier. It is a safety critical system earlier. The safety is overriding factor. Then there are number of components, they are interacting with each other. They are much higher compared to a normal system. human interaction is there is a lot of human machine interaction helps some decision making and all. So it is there, and then there are redundancy, because it is a complex system. Single component or single channel failure should not affect my operation. The redundancy, diversity, and fail-safe criteria, they should be built. So that's how visualizing a not only number of components, its interconnection, okay, and its operation, and they are not linear in all domain. Like a simple component, they will have a linear relationship, but they don't have a linear relationship. So we have to have that kind of diagnostic mechanism, electronic system. So redundancy in monitoring and protection bias. So this is one of the characteristic of K out of N. That means at least K number of channels or components are required out of N for having a normal operation. Okay. So success criteria. If failure criteria, if 2 component fails out of N component, then the system fails. That is, so it depends how you define the configuration in failure domain or in success domain. Then diversity, diverse system, diversity form part of the thing. Diversity means redundancy is one thing, similar line at 3. But diversity means you are having components or channels or system operating on fundamentally 2 different principles. Okay? So that is called diversity. That means the cause for failure here and here, it will not be the same phenomena will not be. It is thing at plant level. If I have built 2 systems and another one is diverse system, that means it's an operation of mechanism totally different from the first principle. Let's say a redundant system is operating by fall of safety devices. A diverse system will be operating not by fall. It will be injection of certain fluid into the system to bring the system to the safe state. So this is called diverse system operating entirely on different principle. Then provision of defense against perceivable and postulated common cause failure. So on one hand, we say that common cause failure is a serious thing and it should be looked into it. But that doesn't mean there are provisions are not there. In the plant, there are provisions made like separation between 2 redundant modules, so that if any fire or flooding is there, both the modules will not get affected. So there is a physical separation. I'll show you in some way or the other how we implement this. Independent source of power. Suppose if all the redundant component, they are being fed from the same source, then common cause failure is the moment that particular source fails. So in redundant system, the similar items, they operate from different source of power actually, or different location of power, So then scheduling maintenance to reduce the human error. In fact, maintenance is staggered maintenance, or the maintenance philosophy, they are such that, let's say simple, in one day all the 3 redundant system will not be maintained, or maintenance activity will be carried out, because mistake happening at 1 can happen at 2 and 3 also. So if we do it in a staggered manner, in the sense that on one equipment you do it today, next month or next 15 days, third one so same common cause will not affect, or same crew or same tools or same thinking process will not affect all the 3 redundant system. Location module to guard flooding, fire. I mean, if I want to safeguard against common cause failure, I will be locating equipment in different location, not only different location, but different elevations also. Because let's say flooding is there in the lowest location, if I have one redundant unit at the other top location, that will not fail, at least that will work actually. And fire, there should be separation, So these are the things, and this is how safety philosophies are implemented in complex engineering system. Imagine we had one parameter, that is CP1 primary system. Okay, let us say first is we are monitoring the environment, because it is electronics, and then these are the sensors. This is a sensor. So it is a channel A, channel B, channel C. So same parameter is being monitored by 3 channels. Okay. So then we have a like usual sensor. After sensor, we have data acquisition system, channel A, channel B, channel C. So here we are having 3 channels monitoring the same parameter. So we can say there is a redundancy. This channel is also doing the same job, this channel is also doing the same job, and this channel is also doing the same job. Advantage is one channel failure doesn't affect my operation because my logic is 2 out of 3 control protection logic. That means as long as 2 channels are operating, it doesn't get failure. Second advantage is I am able to do maintenance also on one channel without affecting my plant operation. So, and then safety, of course. One channel failure will not affect our system because 2 channels are in majority voting, 2 are working properly out of 3. So my system output will go and it will not get affected because the moment this channel is banned, the output will be generated from these 2 channels. Okay. But we said all the 3 channels are same. That means they might get affected by a single cause. Let us say, so what I should do? I should have separation between these channels. So this is a physical separation to reduce the chances of common cause failure, and this is done in real time plant also. These channels either they are located at different location, different rooms, so that there is a isolation. Okay. So now imagine if suppose there is an increase in humidity in this room, let us say this before this partition up, then only this channel will be affected. But if this separation is not there, then it will be affect all the channels. So that will lead to a common cause. So we are trying to separate out common cause failure. Okay. So this is between among these 3 channels, but the same function. It is a primary. We have a diverse function because suppose if this because of some common cause reason this channel fails. So as I mentioned, the second safety system is built upon the diverse mode, totally different fundamental principle. Okay. So this is there. So with this common cause, this will not be get affected. If there is a common cause here, but this is primary. So if there is a failure here, automatic signal will go to take care, or it is online always. So these 2 diverse system monitoring the same parameter, or these 2 system, if this fails, then this will actuate, my control output will go. So there is a redundancy and there is a diversity for this system, and this is how systems are built for complex engineering system. You won't find this in normal systems, or I would say the systems which are not safety oriented, or where the safety is the overriding factor. So this is the kind of caution being design provisions are made. In fact, in many plants you will find not only 3, 4 channels also. Okay. Because if one channel fails, we are totally depending on two channels. So, it is something like you are trying to have more resilience against failure. So, 3 out of 4. Now it depends how you get your reliability get saturated, whether in 2 out of 3 or 2 out of 1. But reliability or safety is the prime importance. Now let us do some common cause failure mapping. Before that, let us understand electronic system quality ensured through specification like American military standard. Okay, if you don't have national standard, mill grade component. Mostly quality is assured through buying a component which is mill grade. So I am in some sense I am reducing the chances of common cause failure, because procurement has to be done to build a system. But if I buy a quality system, the chances of failure or affecting the reliability of the system is less. Then testing as part of procurement is also measured. Now, like you saw previous system, where, yeah, there is one more thing which is there. These systems, they are tested by system alone. Automatic signals are sent, and they are when the that means there is a continuous testing which goes on into the safety system, especially electronic system. You will generate a signal at this end, and you send it here, and response will come back here. So this complete channel will be monitored that this channel is functioning. This is especially true if this channel is doing a function of safety. In safety system, they are in passive mode till the demand comes. So for safety system, monitoring of the let's say if I give one small impulse and test it, the in between component or modules, I obtain the desired output, and then I'll say it is healthy. If the desired output doesn't come, this is called periodic testing module. Here also periodic testing module. So you send a small impulse and test the complete channel. You have found a beautiful way of checking the availability of the safety channels also when they are not active. Okay. So that's how the safety is ensured even for passive mode, especially safety system, because process system, they are on always. If any deviation is there, you will come to know. But in safety system, you will not come to know because they are not having active channel. Of course, arrangements are made in the design that some active phenomena is happening around here, but testing periodically, and this periodicity means it is not something like minutes or hours or days. It is some second, 1 second, one pulse will go. So perpetually we are monitoring the health of the system in continuous mode actually. You know, if any fault is there, it will get displayed on the control room or the panel itself. So here we are trying to say is that testing the system in situ, in the location. Okay. Failure mode effect analysis, this is one more thing. There should not be any failure mode left out which did not form part of our coverage. Reliability analysis at the plant level and meeting reliability at risk level. So for all these systems, it is very much required in a complex design system that reliability target and safety target should be met. So at system level, at the plant level also. Individual protection system unavailability should be, so it's just a quantitative figure. For some standard, I would have got it. So 1 into 10 to the power minus 5. If it is a single channel, the failure probability you can imagine should be less than or equal to 1 into 10 to the power minus 5 per demand. It can be around also, but it should not deviate too much. Similarly, for a complex, let's say nuclear plant, the failure of this thing should be 10 to the power minus 5 per year. 1 into now you can if you compare with other systems, probably you will find that the kind of inbuilt safety into the system is so high that we get this probability, you know, and they all make up from component to system, like electronic system, from system to plant, and that's how it is reflected here per year, 10 to the power minus 5. Even though the plant design ensures resilience, please note all of you, against the common cause failure through various defense mechanisms like redundancy, diversity, independence, power supply separation, human factors, consideration, software reliability. In many safety critical systems, the digital protection is used along with some redundancy or diversity. Why? Because a software failure can disable, because imagine if the same software on a three digital channels are operating, any combination of input fault and some failure occurs, it will be a common cause failure for all the three. So always one has to guard, and you provide additional arrangement either through analog or maybe even another digital system built on different principles altogether. So that is the thing one has to ensure when electronics are this thing. So now let us say we are talking about plant. We carried out a risk assessment of the plant, and so many common cause list was there with us, common cause failure list was there, which has come up on top, you know, importance very high, high rather. though it is rare but relatively high. So human affect which group? This group, and this group. They are called common cause component group. So I have just written here, I am not giving the specific details here, and group 1 to group n, these are the so many things, and for some temperature is they are giving. So see here I am saying it is not getting affected by temperature, some common cause group. Let us say hardware component, they will don't get affected by temperature, but if it is an electronic system, yes, temperature also will play a role in some group. And then humidity, again temperature and humidity, high sensitivity for electronics actually. Flooding. So I have not given the complete this thing, I can map it here. And what will happen if I map it? I have a physics of failure approach. I can work on, see, common cause failure is a phenomena. Defense against that is again a phenomena. We have reduced the possibility, but at the end of the day, I will have to understand all the common cause failures and through physics of failure approach, so that this thing become irrelevant. I will through robustness, through some protection at that level, or through some separation at that level, I will reduce the whatever POF model or root cause analysis model says. So what an elegant mechanism we have here only. Probabilistic mode, we got this information. Now this input we give it to physics of failure consideration or root cause analysis, and we find this is the cause. Humidity affects these three things. So what we should do? Should we provide any barrier, or we should locate in the case? I mean, the sky is open if we understood the cause for failure. If it is a quality related failure, then we will check the quality of the component at the end before it goes into the plant. If it is a maintenance related issue, like maintenance means either human or some parts which have not gone wrong and which is potential for common cause failure, there is some experience is there. If it is there, then we take action. Institutional failure, electromagnetic. Electromagnetic is a phenomena which can affect the system in an adverse manner, and it does not have to introduce the system, and so one has to, so in common cause failure, in the configuration management itself, these things are ruled out. The signals, if it is there, it will get attenuated and the effect will be negligible or no failure. So fault tolerant approach for electronics design and all. So I am just giving you one example how common cause failures are handled. So Markov model is the popular approach, and then I am making this 2 out of 3 failure. I am doing that means handling all the channels in. You saw the 3 channels they are operating and all that. So 2 out of 3 I consider, when the 2 channel out of 3 channel fail, I call it a failure. So suppose if I have 3 channels, and then the assumption is protection and control system comprised of 3 redundant channel. Okay, the failure criteria is 2 out of 3, 2 channel out of 3 channel, or only 1 repair station. Okay, and I have assumed here one more thing, that the failure rates are, say, average failure rate I am applying for simplifying my model. So in Markov there are you will understand when you see the next slide actually. There are P1, P2, P3, 4 condition. P1 condition means all 3 out of 3 they are operating and system is healthy. In P2, 1 out of 3 failed. So that means we have 2 operating. System it is failed but compromised. Margins are reduced. And P3 is 2 out of 3 channel failure, system failure, and 3 out of 3 failure system. So that means this 3 out of 3 failure means there is something common cause. So common cause, and 2 out of 3 I declare the system to be failed. Okay. So if I have to model this system, what I do? So as I mentioned, P1 is the healthy state, P2 is the compromised state. Okay, and I have let us see, P1, P2 are operating states. Okay, because even if one component failure, we have operating state, and there are 3 channels. So there can be 3 more, any of the channel can fail. So 3 mode, and then P2, 1 channel is repair. We can only repair 1 channel. So that's why mu is 1 only. P3 is a failed state. So, I have concentrated them into 3-state module P1, P2 and P3, because common cause also takes system to failed state, and 2 out of 3 also takes to the failed state. So, the P3 is called as a failed state. Exponential distribution we have used, and all the channels have same failure rate, that is average failure rate, mu is repair rate and lambda c is common cause failure rate. So, this information, and we saw how the 3 channels they operate and what is the failure criteria, 2 out of 3. So, I will write a state space equation. Probability of being in state 1, and if rate of change of migrating from that state to the other state. So, dp1 by dt, that is probability of change in probability of this state, is minus 3 lambda. So, minus, that means it is departing from this state. So, minus 3 lambda plus mu returning to this state. So, this is the system we have. So, first equation of the system, that is they are called Markov equation or state space equations. dp2 by dt. So, dp2 by dt for this state, this is a outgoing state, that is, and this is again outgoing and this is incoming. So, 3 lambda will be plus incoming state and minus 2 lambda minus mu, minus 2 lambda minus mu. So, that will define rate of change of this state, dp2 by dt and this one, and third one also dp3 by dt. So, the 3 state means here these 2 states are joining, it is called absorbing state, you know, dp3 by dt 2 lambda plus 3 lambda c, 2 lambda plus common cause failure, 3 lambda c. Actually, this should be lambda c only. There should not be 3 lambda c, because we are saying common cause failure, all the 3 channels have failed. Okay. So, here this 3 will go out. Please correct in your this thing. This equation can be solved for arriving at probability of system failure rate. I have written the differential equation. You can use any method, algebraic method, or you can say these are very simple equation. You can say and find out the probability of system being in P1, P2 and P3. Our interest will be failed state, this is P3 state. So, that we can find out. Okay. You can use matrix method also, you can use algebraic methods also, any method you can use and solve it. Okay. So, week 4 electronics PHM, we have seen interesting features of redundant system, diverse system. We have seen precursor parameter, how they are for which the mode, what is the precursor parameter, for which sensor, what are the degradation attribute we should monitor, role of common cause failure in complex engineering system, sensor failure and common cause failure, why environmental modeling, and finally the common a Markov model to account for failure, repair and common cause failure. So, probably you would have understood now by this time that it is not only a electronic component, but it is basically a channel, that means starting from sensor to final actuation system. You can monitor, and their combination and then common cause failure, what effect, and human factor, what effect it has got. Probably it was pretty clear in this. Now, I will touch upon this electronics PHM when I have dedicated week for electronics, prognostics and health management, because there are many subtle aspects that we need to discuss over there as part of the system. Thank you.